this last idea that we're going to look at is creating new polynomials. And I guess one of the reasons you might do it is, say you had to find, I don't know, the sum of the roots squared. Let's pick a standard one. And you go, well, a bit hard for this one. Maybe I'll create a different polynomial that instead of having roots alpha, beta and gamma, has the roots alpha squared, beta squared, gamma squared, and then I've just got to look at the sum of the roots of that polynomial. So that's one of the reasons you might do it. So if you know alpha, beta and gamma are the roots of a particular polynomial, and you want to create a new one, say it might have been the reciprocal ones that you want to find. Basically how you do it is you mimic the new root. So I'll let y equal 1 on x. So the root, if you like, is the x. So the solution, right? So x is the solution. So that's where I've placed it. Then I'll rearrange it and make x the subject and substitute it into the original equation. And that should come up with a new equation which then has solutions 1 over alpha, 1 over beta, 1 over gamma. If it was some constant times beta, don't know why you do it for something like this, but anyway, you could, of course. Same idea. Oh, well, I'll let y equal some constant times x, rearrange it, x equals y divided by k, substitute it in. Maybe it's plus some constant. So again, let y equal x plus that constant, rearrange it, substitute it in. And the one I was just talking about, the square, this one's a little bit more fun. You get y equal x squared, so x then becomes y to the power of a half, substitute back in, but then you usually got to play around with it because you've now got powers of a half, and of course that's not a polynomial. So all right, let's work with this cubic, alpha, beta and gamma. We're going to create one. Well, let's do the reciprocal. So I'll let y equal 1 on x, so x is 1 on y. Substitute it in. Now, as that stands, that's not a polynomial. So I'll multiply everything by y cubed, bingo, there's my new equation. And that would have solutions of 1 on alpha, 1 on beta, 1 on gamma. It also means things like this, nice questions that could be asked would be like, well, if we know, or I don't know, let's pretend, I'm trying to think what would be a solution to that one up there. Oh, I don't know. Let's say 5, it's not, but let's say 5 is. So if I know 5 is a solution to this one, I can then conclude 1/5 is a solution to this one. Let's do one of these ones. So y equals x plus 1, x equals y minus 1. Substitute in. Well, yes, that is a polynomial, but if I want to play around with the sum and product of the roots, I need to make it look like a polynomial with each individual term. So expand out and group, and there's my new polynomial. Now, where this one can sometimes be handy is because, have a look at this. I know one of the roots of this equation straight away. What is it? 0, yeah, because look, it's got a common factor of y. So I can factorise that out. Y equals 0 is a solution. So therefore I now know a solution to the original equation. Because remember, this is the original root plus 1. So if 0 is the original root plus 1, then the original root must have been -1. So I now know -1 actually is a solution to the original equation. Let's do the square one. So y equals x squared, x equals y to the half. Notice I wrote it as y to the power of a half rather than the square root of y. I just find it easier dealing it that way. So subbing in, and we certainly don't have a polynomial. So how do I get rid of these fractional indices? Well, the common answer would be to square it. Problem is, remember, when you square it, you also get twice the product, all those combinations. If I go 2 times 2 times y to the half, I've still got power of a half. So it's not going to help me. So before I square, I rearrange it. And I move everything that doesn't have a fractional power to the other side. That then means I can factorise out the lowest power, and the bit that's left, in this case, it is y to the power of a half. Now I can square both sides and I have no fractional powers. So I'll get y times y plus 1 squared is equal to 4. Bring everything back to the left-hand side. I've now got my new polynomial. 1 on alpha squared. Now I could do it 2 ways, by the way, before I do it this way. Having just worked out the equation that has roots alpha squared, beta squared, gamma squared, I could now say, well, let's do the reciprocal of those roots and create a third equation. That would work. I'm going to go back to the original one and say, well, let y equal 1 on x squared. So now y is to the power of -1/2. But it's still the same idea. Substitute it in. Anything that doesn't have the fractional power, I'll put to the right. When I square this one, you'll notice the negative power. I don't want a negative power. So before I square it, I've moved it to the other side. So I've divided both sides by y to the negative 3 on 2. Or another way of saying that is timesing by y to the 3 on 2. Square both sides, and I come up with a polynomial. So let's go back to that square one. So yeah, there's the standard question. Find alpha squared plus beta squared plus gamma squared. So if I go back to the original equation, I can say, oh yeah, sum of the roots 1 at a time squared, minus 2 times sum of the roots 2 at a time, substitute in, and I get negative 2. And that's probably how I'd do it 9 times out of 10. But if I have worked out that other equation, then it's going to be a lot easier just to say, oh well, what's the sum of the roots of this new equation? So it'd just be minus b on a of our new equation. Oh, that's negative 2. And it comes out. So it provides a neat little way of finding those sort of ones. Would I do it that way? No. I'd only use that if I've already got the equation, because obviously doing sum of the roots 1 at a time squared minus 2 times something, it's going to be quicker than creating a new equation and doing that in. But if I have already found that equation, I'll make use of it. Okay. So Cambridge 5C. A Patel. Ooh, quite a few out of Patel there. 5E.